Hi, my name is Sanjay. I'll be going over the Physics 172 Spring 25 Exam 2. So problem 1 states, a planet moves in an elliptical orbit around a star located at X. What is the sign of the incremental work W done by the star on the planet as it moves at various points in the orbit? Select the closest answer. So the first thing I'm going to do in this problem is identify our system and surroundings. Our system is our planet, and our surroundings are the star at X. From the energy principle, we can say the change of energy of the system is equal to the work done by the surroundings. So we have change in kinetic energy plus change in potential energy is equal to the work done by our surrounding, which is our star, and our potential energy will end up being 0 in this case. So now we need to recall our definition of work. Work is equal to force times distance, so F times the change of R, which is equal to F times delta R cosine theta. And we know that when theta is less than 90 degrees, cosine theta is greater than 0. When theta is greater than 90 degrees, cosine theta is less than 0. And when theta is equal to 90 degrees, cosine theta is equal to 0. And that will help us indicate our sign of the incremental work W. So now we need to identify points that are moving away, points that are perpendicular, and points that are moving closer to our star X. So let's start off with our first case. Moving away. It is moving away at points 5 and 6. Second case is when it's perpendicular. And that will be at point 3 and 4. And our third case is moving closer. And that will be at points 1 and 2. Now that we have that established, we can draw in our force and displacement on our graph they provide us. So let's start with point 3. So we have our change in displacement, and we have our force acting inward from gravity. And that will end up being a perpendicular relationship. So theta is equal to 90 degrees. And so from that, we can say theta is equal to 90 degrees. Therefore, the work is equal to 0 at points 3 and 4 because cosine theta is equal to 0. Let's look at our first case where it's moving away at 5 and 6. So let's take 6 for example. We have our change in R, and we have our gravitational force. And we see from here that theta is greater than 90 degrees, and it's moving away, which means theta is greater than 90 degrees. Therefore, work is less than 0 because cosine theta is less than 0. Our last case, where it's moving closer, let's use point 2 for example. We have our change of R going to the left, and we have our gravitational force. And we can see here that our theta is less than 90 degrees. So theta is less than 90 degrees. Therefore, the work at 1 and 2 is greater than 0 because cosine theta is greater than 0. And after we do this, we determine that choice A is the correct answer. Work is greater than 0 at points 1 and 2 work is less than 0 at points 5 and 6, and work is equal to 0 at points 3 and 4. Problem 2 states, a Ferris wheel is a vertical circular amusement ride with radius r is equal to 6 meters. Riders sit on a seat that swivel to remain horizontal. The Ferris wheel rotates so that the riders move at a constant speed, v is equal to 8 meters per second. Consider a rider whose mass is 90 kg. How much work does the force exerted by the seat do on the rider as they move from point H to point B? The magnitude of acceleration to gravity is 10 meters per second squared. Select the closest answer. So first thing I'm going to do is identify our system and surroundings. Our system is our rider plus the earth. Our surroundings is the seat. And from that, we can say that from the energy principle, the change of energy of the surroundings is equal to the work done by a surrounding. So we have kinetic energy, the change in kinetic energy, plus change in potential energy from the earth is equal to our work done by our seat. So we have 1/2 m v final squared minus v initial squared for the kinetic energy of our rider, plus mg delta y is equal to the work done by our seat. We know that the rider moves at a constant speed of v is equal to 8 meters per second, which indicates that vf is equal to v final, which is both equal to 8 meters per second. So from that, this will end up canceling out to 0. Now we define our delta y value. So our starting point is h, and that will be at -6, 0, because this is our radius r, and I'll call that start. And our ending point is b, which is at coordinate 0, 6. And let's call this end point. So from that, we can say that delta y is equal to y final minus y initial, which is equal to y at point B minus y at point H, which is equal to 6 minus 0, which is equal to 6 meters. So we can plug in our values, and we can say from that, the work done by our seat is equal to the mass, 90 kg, times gravity, 10 meters per second squared, times our delta y of 6. And from that, we will get that it is equal to 5,400 kilogram times meter squared per second squared, which can also be written as 5,400 joules, and this will correspond to answer choice E. Problem 3 states, you begin with a liquid of mass 2.5 kg at room temperature in a not very well insulated container. You stir the liquid until a thermometer shows that its temperature increased by delta T is equal to 0.4 Kelvin. In the process, you did work of 5,300 joules on the liquid by stirring it. The specific heat capacity of the liquid is 3,800 joules per kilogram per Kelvin. What is the magnitude of the heat transfer from the liquid to its surroundings due to temperature difference that occurred while you stirred? Select the closest answer. So for this problem, you consider conservation of energy. So we have that our work is equal to 5,300 joules given to us, and that is the amount of energy put into the liquid by our stirring. We also have Q, in this case, will be the energy that is actually worn by the liquid. And we know by definition that Q is equal to MC delta T, where C is our specific heat. So that is equal to our mass, 2.5 kg, times our specific heat, which should be joules over kilogram times Kelvin times delta T of 0.4 Kelvin. So we cancel out our units. We will get our Q value is equal to 3,800 joules. Now this is not the answer for our magnitude of heat transfer. Our magnitude of heat transfer, Q, is going to be the amount of energy that has left the liquid as heat. And that will simply be the difference between our work minus Q. So 5,300 joules minus 3,800 joules. So that gives us a final answer for the magnitude of heat transfer as 1,500 joules. And this will correspond with answer choice D. Problem 4 states, a block of mass Ma is 2 kg and specific heat Ca has an initial temperature of Ta. It is brought into thermal contact with a second block of mass Mb is 10 kg and specific heat Cb at initial temperature Tb. When the two blocks have come to equilibrium, they are at temperature T. Block A's temperature has changed by delta T A is equal to 6 Kelvin, while block B's temperature has changed by delta Tb is equal to 9 Kelvin. What is the ratio of the specific heats Ca divided by Cb? Select the closest answer. We know by the conservation of energy that the heat transfer that is lost plus the heat transfer that's gained is equal to 0. And from that, we can say the magnitude of the heat transfer of A, Qa, is equal to the magnitude of heat transfer of B, Qb. And we know by definition that the heat gained or lost by a block is Q is equal to mc delta T. And from Qa, we have Ma, specific heat A, times the change in T. And this is the same as delta Ta. And for our heat transfer of B, it's equal to the mass of B times specific heat of B times the change of temperature, T minus Tb. And that is delta Tb. And we know from equilibrium that energy is conserved, so we can say MaCa times the magnitude of the change in temperature of A is equal to Mb times specific heat of B times the change in magnitude of Tb. So we can plug in our values. We get 2 kg times specific heat of A times the magnitude of change of temperature in A times 6 Kelvin is equal to 10 kg times specific heat of B times delta Tb, which is 9 Kelvin. So we can set up our ratio and we get that Ca over Cb is equal to 10 kg times 9 Kelvin divided by 2 kg times 6 Kelvin. The units end up canceling out since we're dealing with a ratio. And we get that our ratio between the specific heats CA divided by CB is equal to 90 over 12, which is equal to 7.50. And this will correspond to answer choice B. Problem 5 states, a spherical toy has mass 0.6 kg and radius 0.1 meters. A string is wrapped around the toy and the other end of the string is attached to the ceiling. The toy is suspended from the ceiling with the string and then let go from rest, with the string vertical. The spherical toy rotates as it moves vertically downward with the string unwinding around circumference without slipping. What is the angular speed, omega, of the rotating spherical toy after it has fallen a distance h is equal to 0.9 meters in the vertical direction? Select the closest answer. Assume that the magnitude of acceleration due to gravity is g is equal to 10 meters per second squared. Moment of inertia of the spherical toy is I is equal to 2/5 mr squared. So the first thing I'm going to do is identify our system and surroundings. Our system is our toy, and our surroundings is the earth due to gravity, and our string. So if we draw a free body diagram, we have from the center of mass, mg acting downward, and the force of tension acting upward, as shown here. And our coordinate system is positive x and positive y. By the energy principle, we can say that the change of energy of the system is equal to the work done by the surroundings. And from that, we can say that the translational kinetic energy plus rotational kinetic energy plus a change in internal energy is equal to our work done by surroundings. To solve for the translational kinetic energy, should we use point particle? So I will leave a question mark next to that. So in this case, the change in translational kinetic energy is equal to our F net times our change of distance about the center of mass, and our F net ends up being the sum of forces in the y direction is equal to Ft minus mg in the y direction, and our change of y, delta y, is equal to y final minus y initial. So our y initial is equal to h, and our y final is equal to 0. So that will end up giving us negative h in the y direction. So if we rewrite this, we get our vector 0 ft minus mg 0 times 0 minus h 0. However, we have one problem. We don't know what ft is. So ft is unknown. Therefore, in this problem, we cannot use point particle to solve for our k-trans. So I'm going to draw equation 1 right here. So we're going to rewrite equation 1 now. We have 1/2 m v final squared minus 1/2 m v initial squared for our delta k trans plus 1/2 I omega squared minus 1/2 I initial angular speed squared plus our change of internal energy, which ends up being 0 in this case, is equal to our work done by gravity plus our work done by string. And we are given in this problem that the string is let go from rest, which means that V initial, V naught, is equal to 0, and omega naught is equal to 0 also. So we can cancel out those terms to be 0. And we also know that our work done by string, work is defined by force times distance, will end up being 0 in this case, and we have work due to gravity, which acts a distance of h. So if we rewrite this, we can say 1/2 m, and we also know that the string is unwinding without slipping. This will indicate to us that V is equal to omega r. So we have 1/2 m times omega r squared for our translational kinetic energy, plus 1/2 times the inertia, which they give to us as 2/5 m r squared times omega squared, is equal to our work done by gravity. So our F net due to gravity is minus mg acting in the y direction, times our delta y, which we calculated earlier, seen here, to be negative h. So we can rewrite this as, actually before I rewrite it, we can cancel out m in this case, because it's on every side of the equation. We can rewrite that now as 1/2 omega squared r squared plus 1/5 omega squared r squared. So we have common terms on the left side is equal to gravity times h, because the negatives cancel out. After doing some algebra, we can determine that our final angular speed is equal to the square root of 10 gh over 7r squared. And when we plug in our numbers, we get the square root of 10 times 10 meters per second squared times our height h, 0.9 meters, divided by 7 times our radius squared, 0.1 meters squared. And when we simplify that, we get that omega is equal to approximately 35.9 radians per second. And this will correspond with answer choice B. Problem 6 states, 4 objects, each of mass m, are attached to a disk of mass m and radius r as shown. Each object is at a distance b from the axis of the disk. The system is initially at rest on a frictionless flat surface. A string is wound around a disk such that when the end of the string is pulled with a constant force F, the disk both rotates and translates. When the end of the string is pulled a distance w plus d, the center of mass of the disk and 4 masses attached to it has translated a distance d. What is the angular speed omega of the system at this instant? The moment of inertia I disk is equal to 1/2 big M r squared. The moment of inertia of a point mass is I is equal to small m small r squared. So the first thing I'm going to do is write out our system and surroundings. Our system is our big mass m plus 4 times the small mass. Our surrounding is our hand or our applied force F. From the energy principle, we can say the change of energy of the system is equal to the work done by surrounding. For point particle, we have that the change in translational kinetic energy is equal to our F net times change in R about the center of mass. So in the x direction, our F net is just our applied force, and our change in R about the center of mass will be a distance of d. So our translational kinetic energy is simply Fd. Now for our extended system, we can write this as the change in translational energy, which we just calculated, plus the change in rotational kinetic energy is equal to our work done by our hand, which I'll denote as a subscript of h. So we also have to consider the total inertia. I'll call it I total is equal to our disk, 1/2 mr squared, plus 4 times our point mass, so 4 times mb squared, since the distance here is denoted by b. So now that we have that, we can rewrite this as Fd plus 1/2 times the inertia omega minus 0 squared. And the reason why our initial omega is 0 because it states the system is initially at rest, which will indicate to us that omega initial is equal to 0. And we set that equal to our work done by our hand. So our work done by our hand is the force times our distance, which is W plus D in this case. So now that we have that, we can rewrite that as Fd plus 1/2 I omega squared is equal to Fw plus Fd. And we see that Fd cancels out on both sides. So we're left with 1/2 times the inertia omega squared is equal to F times our distance W, not to get those mixed up. And when we rearrange in terms of omega, we get that it's the square root of Fw divided by our inertia, which is equal to the square root of 2Fw over 1/2 mr squared plus 4mb squared. And in our answer choices, they get rid of the 1/2 in the numerator for the mr squared term, so we're going to multiply everything by 2. So when we do that, we're going to say multiply by 2. We get 4Fw over mr squared plus 8mb squared. And this will correspond to answer choice A. Problem 7 states, a cylinder of mass 4.2 kg and radius 0.2 meters is released from rest at the top of an inclined plane. The cylinder rolls down the plane without slipping. What is the cylinder's angular speed, omega final, when it reaches the height, h is equal to 1.2 meters, below its initial position? Select the closest answer. Note, moment of inertia of a cylinder is 1/2 mr squared. Magnitude of acceleration due to gravity is 10 meters per second squared. So the first thing I'm going to do is identify our system and surroundings. Our system is the cylinder plus the earth. And our surrounding is the ramp. Now that we have that, from the energy principle, we can say the change of energy of the system is equal to the work done by the surroundings. So we have the translational kinetic energy, change in that, plus the change in rotational energy, plus the change in internal energy. On the left-hand side of our equation, change of energy system is equal to F dot the change in distance. And from our ramp, it is frictionless and the normal force does not do any work, so that will end up canceling to 0. We know that the translational kinetic energy is 1/2 mb squared. The change of that is equal to 1/2 m delta v squared, which will just be 1/2 mv final squared, since it's initially at rest. So you can say V initial is equal to 0. And from our problem statement, the cylinder rolls on the plane without slipping, which will indicate to us that the velocity is equal to omega r. So we can rewrite our changing translational kinetic energy as 1/2 m times omega final r squared. And now for our rotational kinetic energy, the change of that is equal to 1/2 times the inertia I times the change of angular speed squared, omega squared. And we know since it's initially at rest, we can also say that omega initial is equal to 0. So we can rewrite that as 1/2 times the inertia 1/2 mr squared times omega final squared. And now we have our change in internal energy is equal to the change of potential energy of the system due to gravity, and that will be equal to minus mgh. And you might be wondering how we get minus mgh. So delta y in this case is equal to y final minus y initial. And this is where we need to define our coordinate system. So we have positive x and positive y. Here, y final is equal to 0, and y initial is equal to h. So from that we can say is equal to 0 minus h, which is negative h. Now that we have that, we can plug that back into our energy principle equation. So we have 1/2 times m omega final r squared plus 1/2 times 1/2 mr squared times omega f squared is equal to mgh if we remove it on the other side. So now that we have that, we can cancel out our masses since they're on both sides of our equation. And we can rewrite this as 1/2 omega final squared r squared plus 1/4 omega final squared r squared is equal to gravity g times h. So we have 3/4 omega final squared r squared is equal to g times h. And from that we can say that omega final is equal to the square root of 4gh divided by 3r squared. And when we plug in our numbers, we get root 4 times 10 meters per second squared times our height of 1.2 meters divided by 3 times the radius squared. So 3 times 0.2 meters squared. And that will give us approximately 20.0 radians per second. And this will correspond to answer choice D. Your friend of mass m jumps up from a crouched position to a vertical standing position such that the center of mass moves vertically upward through height h. During this process, the point of contact between your friend's feet and the ground is stationary. Your friend experiences a normal force Fn acting upward at the point of contact between the feet and the ground. Your friend's change in translational kinetic energy, a center of mass, is delta K trans. The change in internal energy in the process is delta E int. And the change in kinetic energy due to the torso, moving relative to the center of mass, is delta K rel. Acceleration due to gravity, g, is downward. Ignore air resistance. Which of the following equations represents the energy principle of the extended system as applied to your friend from the initial to the final position shown above? So first thing I'm going to do is identify our system and surroundings. Our system is our friend, and our surrounding is the earth, gravity, and the ground. So from that, we can say, from the energy principle, the change of energy of the system is equal to the work done by surrounding. So our system, or our friend, has a changing translational kinetic energy of the center of mass. They have a change in internal energy, and they have kinetic energy due to the torso moving relative to the center of mass. So that will be on our left side of our equation. So you can rewrite this as delta K trans plus delta E int plus delta K relative is equal to our work done by the Earth, I'll call that E subscript, plus the work done by the ground. We know by definition that work is equal to the force times the change in distance, delta R. And we know that from our center of mass, let's call this center of mass, we have gravity acting downward. So this is our weight, let's call that mg. So we can say that our work done by Earth is equal to minus mg, since our coordinate system is positive x, positive y, times our delta y. Now we need to figure out our delta y. So our delta y is equal to the final minus initial. And this is our initial is equal to 0 if we start the coordinate system here, x and y. And then our final y is equal to h. So this will be equal to minus mg times h. So the work done by gravity, or the Earth, is equal to minus mgh. Now, it's important to note for our work done by the ground, we have our normal force, let's call that Fn, times our delta y. But in this case, the feet stay on the floor as given in the equation. So let's see here. They said the point of contact between your friend's feet and the ground is stationary. So our delta y will be 0, therefore our work of gravity will be equal to 0. So we can rewrite our equation to get delta K trans plus delta E int plus delta K relative is equal to minus mgh. And for some reason, they put the answer choices on the next page, but this will correspond to answer choice C. Problems 9 and 10 state, you of mass 90 kg hang by your hands from a tree limb that is a height L of 6 meters above the ground, with your center of mass of a height h is equal to 5.0 meters above the ground. You let go and fall vertically downward, such that when your feet touch the ground, your center of mass drops a distance of d is equal to 4.2 meters. You absorb the shock by bending your knees, ending up momentarily at rest in a crouched position with your center of mass a height of b is equal to 0.6 meters above the ground. Assume magnitude of acceleration to gravity is g is equal to 10 meters per second squared. What is the translational kinetic energy of your center of mass at the instant your feet first touch the ground? Select the closest answer. So in this problem, in problem 9, we'll be dealing with 1 and 2, just before it hits the ground at speed v. We know by definition that the translational kinetic energy is equal to our net force, F net, times our change of distance about the center of mass. And if we draw a quick free body diagram, identify coordinate systems as positive x, positive y, and we have our center of mass here, we have the force of gravity acting downward, mg. So from this we can say the sum of forces about y, is equal to minus mg. Our final position will be h minus d, this quantity here that I drew. So if we write it out, we have the change of r about the center mass is equal to our final position, which is h minus d, minus our initial, which is just h. So if we draw that in vector quantity, we have 0, our final h minus d, 0, minus our initial h in the y direction. So from that, we can say the change of r about the center of mass is equal to d in the y direction, negative d in the y direction. So now that we have that, we can say our translational kinetic energy just before it hits the ground at speed v is equal to our F net of minus mg, and this is all in the y direction, times our change of r about the center of mass minus d. So we get positive mgd. And we can simplify that, so that will be 90 kg for our mass times 10 meters per second squared times our distance d of 4.2 meters, and that will give us 3,780 kg times meters per second squared, meters squared per second squared, and that is the same thing as 3,780 joules. So this will correspond to answer choice D. Problem 10 states, what is the change in internal energy in your body from the initial to final position? Select the closest answer. So in this part, we'll be dealing with state 1 and state 3 as shown here. To do this, I'm going to first identify our system and surroundings. So our system is our mass m, and our surrounding we will choose to be the Earth by gravity. Now that we have that, we can say from the energy principle, the change of energy of the system is equal to the work done by the surroundings. And from that, we can say the change of translational kinetic energy plus change of kinetic energy rotational plus our change in internal energy, which we're solving for in this case, is equal to our work done by gravity. We know that another definition for translational kinetic energy is equal to 1/2 m times the change of velocity squared, delta v squared. And we know in this case that we are initially at rest and we are finally at rest. That means the change of velocity is equal to 0. Therefore, our translational kinetic energy will cancel to be 0. And we also have no rotating components in this case, so that can also be crossed out to be 0. From that, we can say that the change in internal energy is equal to the work done by gravity. And we know by definition that our work is equal to the force times distance about the center of mass. And we know that from before, if we draw a quick free body diagram and our coordinate system, positive x and positive y, about our center of mass, we have force of gravity acting downward, mg. So our sum of forces in the y direction is just equal to minus mg. And our change of r will be our final position minus our initial position, which is equal to, if we draw out here, this will be h minus b. So our final position is at b, so it'll be 0, b, 0 in vector notation, minus our initial height of 0, h, 0. So we get that our change of r is equal to 0 b minus h in the y direction and 0 meters. So now that we have that, we can rewrite our work of gravity is equal to our F net in the y direction minus mg times our change of distance in the y direction, b minus h, and we can also rewrite that as mg h minus b if we substitute the negative. So we get that the work of gravity is equal to our mass of 90 kg times gravity 10 meters per second squared times our distance h, which is 5.0 meters, minus distance b, which is 0.6 meters, and that will give us 3,960 kilograms times meters squared per second squared, and that can also be written as 3,960 joules. And we know from our property from before that the change of internal energy is equal to the work done by gravity. Therefore, we can say the change of internal energy is equal to 3,960 joules. And this will correspond to answer choice B. Problems 11 and 12 state, two identical masses at rest on a frictionless horizontal surface are connected to each other with an unstretched spring. Initially, the left mass located at the origin and the right mass located at x2 is equal to 1.0 meters. Then the right mass is pulled with a constant horizontal force of 100 newtons to the right. Eventually, the left mass is shown at location x1 is equal to 0.6 meters. And the right mass is at location x3 is equal to 3.4 meters. What is the translational kinetic energy of the system in the final state? Select the closest answer. We know by definition that the translational kinetic energy is equal to the net force dot the change in the position about the center of mass. So we know that F net, which is given to us as our applied force in the x direction, and that is 100 newtons. For our change in position about the center of mass, I will draw a graph for better visualization. So on the top, we have our initial state. And I'll label this with box 1 and box 2 respectively. So here we have our spring, which I'll denote with a line between the two. This is block 1, block 2, block 1, block 2. This is the initial state. This is the final state. And basically, we want to know the change in position about the center of mass in the middle of the two blocks in the spring, which is our combined system. So let's call this center of mass 1, and let's call this center of mass 2. We know that this is x is equal to 0 meters. We know that this is x1 is equal to 0.6 meters. This is x is equal to 1.0 meters. And this is x3 is equal to 3.4 meters. And this should be x2. So from that, we can say the center of mass 1 is equal to our average x plus x2 divided by 2, which is equal to 0 plus 1.0 meters divided by 2, and that is simply 0.5 meters. And our center mass 2 is equal to the average of x1 plus x3 over 2, and that is 0.6 plus 3.4 meters divided by 2, which is equal to 2.0 meters. We have the change of position about the center mass is equal to our center mass 2 minus center mass 1, which is equal to 2.0 minus 0.5, and that will give us 1.5 meters. We know our equation for change in translational energy as we stated earlier, and we will rewrite that as the product of our F net in the x direction, 100 newtons, times our change in position about the center mass, 1.5 meters, which is equal to 150 Newton meters, which is the same thing as 150 joules. And this will correspond to answer choice B. Problem 12 states, what is the change in internal energy of the system from initial to final state? Select the closest answer. So first thing I'm going to do is identify our system and surroundings. Our system is block 1 plus block 2 plus our spring. And our surrounding is our applied force, F. So from this and the energy principle, we can say the change of energy in the system is equal to the work done by the surroundings. So we have translational kinetic energy plus rotational, and in this case we don't have it, so that'll cancel to be 0, plus the change in internal energy is equal to our work done by our applied force. So our translational energy, which we calculated in the previous question, is 150 joules plus our change in internal energy, which we're solving for in this question, is equal to our work done by our surroundings. So we recall that work is equal to our force times our change in R. And notice that this is not about the center of mass this time, unlike the translational kinetic energy. This change in R will involve x2 to x3. This will be our change in R. So we can rewrite the change of R as our final minus our initial, which is equal to x3 minus x2, and that is 3.4 meters minus our x2 of 1.0 meters, which is equal to 2.4 meters. So that's equal to our force of 100 newtons times our distance of 2.4 meters. So we have that the change in internal energy is equal to 240 joules minus our translational kinetic energy, 150 joules, and that will give us 90 joules. And this corresponds to an answer choice of D. Problems 13, 14, and 15 state, a block of mass 30 kg is initially held at a certain point on an incline that makes an angle theta is equal to 50 degrees, as shown with the horizontal. The block is in contact with, but not attached to, a spring of stiffness Ks is equal to 1,100 newtons per meter, and compressed length L is equal to 4.0 meters. The relaxed length L naught is equal to 7.0 meters of the spring is also equal to the total length of the incline. When you release the block, the spring pushes it up all the way to the top of the incline, at which point it is launched into the air. The coefficient of kinetic friction between the block and the incline is mu k is equal to 0.1. The magnitude of acceleration of gravity is 10 meters per second squared. So before I solve this problem, I'm going to be solving for our V naught that we will use in the following next problems. We will see in problem 13 that our system is our block plus the earth plus the spring. And our surroundings is our ramp that has friction on it. So from that, from the energy principle, we can say the change of energy of the system is equal to the work done by the surroundings. Now, before I do that, I will draw a quick free body diagram of the forces that are present in our system. So we have force of gravity acting downward from block M. We have our spring force acting to the right. We have a normal force acting perpendicular to the ramp. We'll call that Fn. And we have our friction opposing our impending motion. So friction will act to the left on the surface of the ramp, and we'll call that F. And we also know from trig that this angle theta is equal to this angle theta, so we can get our x and y components of mg. Since ultimately we want our coordinate system to be slanted like this. So from that we can say the sum of forces in the y direction is equal to 0, which is equal to the normal force minus mg cosine theta from the trig we did earlier. And from that, we can say the normal force is equal to mg cosine theta. Now we can expand our equation that we derived from our energy principle. So we have our kinetic energy, 1/2 m v naught squared, since it's initially at rest. And we have our spring force, which is minus 1/2 times the spring constant times our displacement squared. And to clarify, our S is this distance or in other words, S is equal to L naught minus L. We also have potential energy from gravity. So we have minus mg delta y. So you might be asking, what is delta y in this scenario? So at the bottom of our block M, let's call that D1 in our initial state. And in our final state, just before it is launched into the air, at the very top, that is D2. Now, our change in y, delta y that we have, is going to be this distance here. This is delta y. So basically, delta y, the change of height, is equal to our final height d2 minus d1. And we set this equation equal to our work done by our ramp. So our force done by a ramp is friction. So we can expand that as mu k times the normal force, which we calculated to be mg cosine theta, times our displacement, which ends up being S. And we previously saw that it is equal to L naught minus L. So now from here, we would solve V naught. However, we still have some unknowns. We do not know what our delta y value is, so we have to do some trig. So if we take our sine of theta, seen here, that is opposite over hypotenuse, so we get d1 over L, and we do sine theta is equal to d2 over our total length, L naught. And so we get sine of our 50 degrees is equal to d1 over our length of 4.0 meters. And we get sine theta, sine 50, is equal to d2 over L naught, which is 7.0 meters. And we can rearrange that to get our d1 and d2 values, which end up being 3.06 for d1 and 5.36 meters for d1 and d2 respectively. So we get that our change of y, delta y, is equal to 2.3 meters. And before I solve for this v naught, I messed up my signs, so it should be positive mg delta y and then minus the work done by friction. And so when we plug in all our values that we have here, d1, d2, delta y, our s, we get that v naught is equal to the square root of 280. And when you take the square root of that, you will get approximately 16.7 meters per second, which we will use for parts B and C. Part A states 3 students present scientific arguments about finding the speed v naught at which the block is launched into the air at the top of the spring. Which is /are correct? So our first claim, they choose the block as a system and everything else as the surroundings. Now let's look at the reasoning. So they choose change in kinetic energy from the block, that seems right. Change in potential energy from the earth, no, because they choose the earth as the surroundings. So that would automatically make this statement incorrect. So statement 1 is incorrect. Now let's look at our second statement. They choose the block, spring, and earth in the system, and the ramp in the surroundings. Their reasoning is that they would have a change in kinetic energy for the block, that sounds right. Change in potential energy from the spring, that sounds right. And a change in potential energy from the earth, that sounds right. And for their surroundings, they have work from friction on the ramp. So that matches up, and therefore that statement will be correct. Our third statement, they choose the block and the spring as a system and everything else as the surroundings, which are the ramp and the earth. Now their reasoning, they say they have a change in kinetic energy from the block, that looks good. And they say work from the spring, which would make it part of the surroundings, which is not correct in this case. Therefore, we can say our last statement is incorrect, and this will match up with answer choice D. And we can say from the statement that the change in kinetic energy in our block plus change in potential energy of our spring plus a change in potential energy from the earth is equal to our work done by the friction or ramp. So from this we have 1/2 times mass v naught minus 0 squared plus 0 minus 1/2 spring constant Ks times our displacement squared plus mg delta y is equal to minus mu k mg cosine theta times our displacement s. And using that, we previously derived for v naught, and that will be approximately 16.7 meters per second, which we will use for parts B and C. Part B states, what is the time duration T max after it is launched for the block to reach the highest height H max on its flight? Assume no air drag. So let's draw a quick free body diagram of where we originally were and where we now are at. So in this free body diagram, we have from our center of mass, we have gravity acting downward, we'll call that mg. We have normal force acting perpendicular to the ramp. We'll call it Fn. We have our spring force acting to the right. We'll call that Fs. And our impending motion is going to the right. Therefore, friction will oppose the impending motion and be going to the left as follows, and we'll call that F. We also know at the bottom of our ramp, we have this angle theta, and if we do some trig, we can determine that this angle theta is equivalent. Therefore, we get our x and y components of mg cosine theta and mg sine theta. So this uses a coordinate system as follows. We'll call that y prime, x prime. However, at our h max, the free body diagram for our block will look different. Since we're no longer dealing with the ramp and spring, we have our box. And from center mass, we have gravity acting downward, mg. And that's our only force acting here. And we have some velocity, v naught, that we calculated earlier, that is going at an angle of theta. So we can say our y component is equal to v naught sine theta, since mg is in the y direction, and our new coordinate system will look like this: positive x, positive y. And recall from earlier in the semester the momentum principle. Which is defined by the change of momentum of the system, or the impulse, is equal to the net force times the change in time. And that's how you can get T max in this case. So we have minus m times v final, which is v naught sine theta, minus our initial velocity 0, is equal to our F net of minus mg times delta t. In this case, the m's will cancel out, as well as a negative. So we can rewrite our expression for the change in time is equal to v naught sine theta over g. So that will be equal to 16.7 meters per second times sine 50 over our gravity constant of 10 meters per second squared. And that will give us 1.28 seconds for our T max, and that will correspond to answer choice E. Part C states, what is the maximum height H max with respect to the top of the ramp achieved by the block? Assume no air drag. So when we're at H max, we have our block, and from our block we have gravity acting downward, mg, and we have our velocity that we mentioned earlier, v naught, at an angle of theta. So we can get our x and y components from that to solve previous parts of this problem. And now we gotta identify our new system and surroundings from this. So our system is our block, and our surrounding is the earth. So from the energy principle, we can say the change of energy of the system is equal to the work done by surroundings. So we get the change of kinetic energy of our block is equal to the work done by gravity. So it's going to be 1/2 m v naught sine theta, which is the y component of our velocity, minus initial of 0 squared, is equal to our mg times delta y. Delta y is equal to our final height minus initial. And with respect to here, y initial is equal to 0, y final is equal to h max. Therefore, our delta y is just equal to h max. Now that we have that, we can rearrange our h max. Now that we have that, we can rearrange in terms of h max. So h max is equal to v naught squared sine theta squared divided by 2 times gravity constant g. And now we can plug in our values and we will get 16.7 meters per second squared times sine of 50 degrees squared divided by 2 times gravity, 10 meters per second squared. And that will give us an h max of approximately 8.19 meters. And this will correspond to answer choice B. Thank you for watching and good luck.